Hi, welcome to the talk for design of a Symbolically executable embedded hypervisor. The slides are quite fully packed, so I'll remove my picture now. I'll pop back in at the end. The idea for this paper is our observation that usually hypervisors and microkernels are built in a very generic way to support lots of use cases, and for that they allow lots of dynamic features at runtime, right? Create new VMs or tasks, reconfigure the memory, assign new IRQ lines, and so on and so on. But our observation is that most embedded use cases, or at least many embedded use cases, actually don't need those, right? So the idea is we build a hypervisor specifically for those static use cases. And we make no compromises on that, so we remove every dynamic element we can find. And we see where we end up. Smaller, possibly. Do we have any special properties with this new hypervisor? And what does that mean for formal analysis? So looking at the standard picture of what you might expect to find in a hypervisor, we can now probably toss out a lot of elements you would usually expect. So let's put up the basket and let's move along. So VM management, probably not needed, right? If we're, like, for example, consolidating lots of VMs which were on different platforms before on one big platform, we know what VMs we want. We won't create any new at runtime. Out it goes. Same goes for memory management, right? We just create all the page tables beforehand. We decide what memory assignments we need. No runtime management. Third part, we won't do online scheduling. So we only have a dispatch, but we create the schedule offline beforehand because we probably know our timing constraints. And finally, we also do the IRQ assignment offline beforehand because we know which peripherals belong to which VM. Maybe we have a driver VM, but that multiplexes, but in the end, no management at runtime. So we also have a fixed IRQ dispatch table. And then we end up with a far reduced hypervisor. This now gets our name, right? So this is Phidias. Actually, it was implemented from scratch and not from a standard hypervisor by removing stuff. So what do we do with all these components we removed? Well, we have to move them somewhere, right? We need to specify what VMs we have, what memory constraints they have, and so on. So those back out from the basket, and we put those into an offline configuration toolkit, which will create the offline schedule, which will do all the memory allocation and placement, will create directly all the binary page table data and only inform the hypervisor where the base addresses are, and also generate all the necessary data structures for that. So, and it looks like this. So we get an XML as input. This is what a system integrator will write. And then the system will run. It creates an enhanced XML with all the address locations chosen, all the IRQ lines created, and so on. We get the binary page table data out and an ELF, which contains all the data structures, which is then linked directly into our statically configured hypervisor. Now, what does that give us? Well, we now have a hypervisor image with a very limited state space, right? Because all objects are known a priori, nothing is created newly while the system is running. So we have a fixed set of path inputs and path outputs, right? And now we can actually do exhaustive symbolic execution, right? We can look at all the paths throughout the hypervisor from boot up to the first reschedule, from a trap to a resume of the same vCPU, and look what that does, right? And try to infer from the input state, which is, as we're talking ARMv8 at the moment, which is usually specified by a certain value in the syndrome register, and the PC, which starts at the vector base address plus a certain offset depending on the type of entry. And we get out on the other side with a symbolic final state, which is formulated right in terms of expressions depending on the input state. And then depending on the exact path, input, output, we can look at certain invariants and by that infer with very little prior work, so no abstract specification writing, no long reasoning, no interactive theorem proving. We can check whether those invariants actually hold. Now, this is all I can tell in this short time frame on the teaser video. If you want, have a look at the full presentation. There I'll present more implementation details. I'll tell about all the architectures and the platforms we're supporting with this. I'll also give a more in-depth description of how the symbolic execution engine is working. I'll give an explanation and a list of the invariants that we're currently checking. And of course, I'll also describe what the shortcomings are. After all, it's an academic project, right? Nothing's perfect. And finally, I'll also tell you what further aspects might be interesting, where the static approach could be beneficial. So, thank you all for watching. I hope you found this interesting. See you in the Q&A. Bye.